Now let's learn about the reactions of hydrocarbons. When it comes to the hydrocarbons, alkenes are the least reactive. Okay. In general, they don't react with strong acids. They don't react with strong bases. Most oxidizing and reducing agents also don't react with them. The only thing that we know that hydrocarbons really do is combustion. In terms of other hydrocarbons like alkenes can actually undergo addition reactions, as we are going to see later. And alkynes, which are the carbon-carbon triple bonds, also can undergo addition reactions. As I mentioned, alkanes can undergo combustion, which is a reaction that we observed previously. But let me clarify. Combustion is not only found in alkanes. Let me just write a note. All hydrocarbons combust, meaning they undergo combustion. And regardless of the number of carbons, what they are going to produce is CO2 and water. We're going to learn later in this chapter about predicting the products. And when it comes to combustion, what I want you to write as a product is just CO2 and water for any type of hydrocarbon that could be combusting. Let's now move on to addition reactions, which addition reactions are going to be specifically present in alkene functional groups. Addition reactions means that we are going to be adding atoms to the carbons that used to be double bonded. In the general reaction scheme, we can see that if you start with an alkene and you have atoms that are going to be added, we're going to break the double bond, convert it to a single bond, and each of the carbons that used to be double bonded is going to receive a new atom. The first type of addition reaction that you need to be familiar with is going to be hydrogenation. In hydrogenation, each of the carbons that used to be double bonded are now going to be single bonded, and each of them is going to receive a hydrogen. So alkenes are converted to alkanes via hydrogenation. This reaction needs a metal catalyst in order to proceed. So at times we see that in these reactions are in the presence of platinum, nickel, or palladium in order for them to proceed. So here we have 2-butene. The carbons that used to be double bonded are now single bonded. And upon the reaction happening, each of them is going to receive a hydrogen. So you synthesize butane. Alkynes can also undergo hydrogenation reactions. But instead of each of the carbons that used to be triple bonded receiving one hydrogen, each of them receive two hydrogens. So the general scheme for hydrogenation of alkynes is the following. You have an alkyne. The triple bond turns into a single bond. Each of the carbons that used to be triple bonded receives two hydrogens. So every time you have an alkyne, you will also produce an alkane, just like we saw in the case of alkenes getting hydrogenated. The catalyst used here, it can be platinum, it could be nickel, or it could be palladium, any of them. So this term catalyst refers to these metals. So we can see in the example below that if we have the following alkyne which has 1, 2, 3, 4, 5, 6 carbons. This is 3-hexyne. If I number the carbons 1, 2, 3, 4, 5, and 6, we see that carbons 3 and carbon 4 used to be triple bonded. Upon the reaction happening, now they're going to be single bonded, and each of them is going to receive 2 hydrogens. So 3-hexyne converts to hexane upon hydrogenation. It is important to note that not all unsaturated hydrocarbons can hydrogenate. If styrene undergoes hydrogenation, only the alkene portion of styrene, meaning this, is what gets hydrogenated. Benzene resists hydrogenation because that aromatic structure, that it is the benzene ring, actually provides stability to the molecule, and it is so stable that hydrogenation is not going to break each of the bonds present in the benzene ring. So understand that benzene rings are resistant to hydrogenation. One of the main skills that you guys need to know for this is, how do I predict the products for a reaction? And we are going to learn how to do that by doing these 4 examples. We can see that if I number these reactions as 1, 2, 3, and 4, reactions 1, 2, and 3 are specifically hydrogenation reactions. I know that these are hydrogenation reactions because I observe that there's H2 as a reactant. It can show up on top of an arrow. It can show up next to a plus sign. As long as you see it in those formats, that means that that is going to be one of the reactants. We can also observe the different organic molecules that we are going to then react under those conditions. First, let's identify what will be the product of the reactions for 1, 2, and 3. In number 1, we have a benzene ring, and there's no other functional group in it. We just learned that benzene rings are resistant to hydrogenation conditions. So it doesn't matter that here it says 3. It could say 5. It could say 10. Hydrogenation is not going to happen when you have a benzene ring by itself in a molecule. The only time that it could react if you have a benzene ring and additionally you have an alkene or an alkyne. So in this precise example, there's going to be no product form, so we say no reaction. On number 2, we have an alkene and we have hydrogenation conditions. What we have is that on the carbons that used to be double bonded, each of them will receive a hydrogen. So typically what we do in order to write the product is that we rewrite the reactant and exclude the double bond. Then each of the carbons that used to be double bonded receive a hydrogen. So if I use my highlighter tool, this is a carbon, this is a carbon. These are the carbons that used to be double bonded. Now each of them received a hydrogen. In example number 3, we have 1, 2, 3, 4, 5, 6 carbons. Carbon 3 and carbon 4 is going to each of them receive two hydrogens. So I have to make sure that when I rewrite my molecule, I include everything that was given in the beginning because I'm not going to change the number of carbons. So I'm going to draw 1 carbon, 2 carbons, 3 carbons, 4, 5, and 6. On carbon number 2, I have 2 methyl groups. Let me just label them so you see. So this methyl and this methyl I'm writing here. Let me just number the carbons. 1, 2, 3, 4, 5, and 6. There's no other substituents in the molecule. Lastly, I'm going to write the 2 hydrogens that are added on 4, the 2 hydrogens that are added on 3, which come from this. And that's how you write the product specifically for reaction 3. Lastly, here we have a hydrocarbon. When we see that this is combining with O2 and heat, this means that a combustion reaction is happening. Those are the reagents for combustion. And when that occurs, how I write the answer for my predicted product is CO2, water, and please include energy, because these type of combustions always release an energy in the form of a flame. The only thing is, please you do not attempt to balance the reaction. All I wanted to see is that you understand that when something combusts, you produce CO2, water, and energy. Next, we're going to look at the reaction that is called hydration. And this specifically will be the addition of water to an alkene. So in this class, we only look at hydration reactions when we start with an alkene. In this reaction, when we look at the overall reaction, how it happens, we're going to have an alkene is going to react with water and sulfuric acid. When that happens, the addition of the atoms is going to be what was present in water. So we have to, just for the purposes of the reaction, think that water is going to split into H and OH. So that's why we observe that in the reaction, once the double bond is broken and we add atoms, the carbons that used to be double bonded, one will receive a hydrogen and one will receive an OH. We can see the example below that illustrates how 2-butene undergoes hydration. If I number the carbon atoms in 2-butene, this is 1, this is 2, this is 3, this is 4. And if I number the product, this is 1, this is 2, this is 3, and this is 4, I can observe that the double bond used to be between carbons 2 and 3. And when I'm predicting the product of this hydration, we can observe that between carbon 2 and 3, we went from a double bond to a single bond. And then here, carbon 2 received the hydrogen and carbon 3 received the OH. In this example, because specifically this molecule is symmetrical, it really doesn't matter who receives the H or receives the OH. But in general, we actually have rules to determine who receives the H and who receives the OH. The rule that determines in hydration reaction who receives the H and who receives the OH is called Markovnikov's rule. And Markovnikov's rule basically establishes that if we have an alkene, and we're going to look at the example here of propene, and then we pay attention to the carbon atoms that are present specifically in the carbon-carbon double bond, the carbon atom that is directly attached to the most hydrogens, meaning if I look at this carbon and this carbon, the one on the left only has one hydrogen. The carbon on the right has two hydrogens. So that means that this one has more hydrogens. Only then I know that the one that has the most hydrogens will get the incoming hydrogen. And then the other carbon that has the least hydrogens will get the OH. So if we look at propene, getting hydrated, you may suspect, oh, one receives the H and one receives the OH. But when you look at what is the product of the reaction, the only product that we observe is this. Because when we look closely at it, this carbon used to have directly attached the most H's. That's why it gained the H. This carbon was directly attached to the least H's. That's why it obtained the OH. Let's do some practice problems to solidify this concept. Here we have two examples for alkenes that are undergoing hydration conditions. So remember, hydration conditions means that we are going to add water in the presence of acid. So the sulfuric acid role in this reaction is going to be a catalyst. In the sulfuric acid, we can write it as H2SO4, or you can write it as H+. It means the same thing. It's just a catalyst. So if we look at the first alkene, let me just zoom in so we can predict the product of that. What happens in this alkene is that when we investigate and we look at the carbons in the double bond, which is this one and this one, we can see that this has one H attached. This has 0 H's attached. So when I'm predicting the product, I rewrite my molecule, and instead of writing the two lines for the double bond, I only write one. So I'm going to write CH3 connected to CH. Now this is going to be single bonded to a C. This is connected to a CH3. This is connected to a CH3. And now, let me also put in the highlight of the atoms. Since the carbon that was in yellow has one H, it gets the incoming H. The carbon that is in that purple lavender color, kind of, it gets the OH. Because remember that in this reaction, basically what you're adding is the atoms in the water, which is just H and OH. Let's do one more example. Here we have an alkene. For those students that skeletal is still a little bit intimidating, add the carbons and hydrogens. So when I do that, this is a carbon connected to two hydrogens. Remember that the reason why I know that that's a carbon connected to two hydrogens is because the end is a carbon. That carbon has two lines. In order to get it to 4 lines, so it completes the octet, it needs 2 hydrogens. So that's why that's a CH2. This is a carbon. It is bonded to 3 lines, so it needs 1 more. So this is a CH. So here, this carbon has 2 hydrogens attached, while this one has 1 hydrogen attached. So when I predict the product, I'm going to redraw the molecule, as given. I'm not going to include the double bond, only one line in it. So this is a CH, single bonded to a CH2. And then the carbon that used to have the most H's gets the incoming H. The carbon that had the least H's gets the incoming OH. And that's how you predict the product in hydration reactions.